Go for it.
Welcome to your Daily Dopamine with Dr. Joe McCullough, where we deliver daily doses of education, entertainment, and inspiration. So sit back, relax, and get ready to be dopamine.
Hey Lily, hey Silver Lining, Legendary Woo.
Yeah.
Tomato, all the regulars are here. Okay, welcome to episode 7 of our weekly Ask a Physicist Anything. My name is Joe McCullough. I'm the physics program chair at Cabrillo College in Santa Cruz, California, and we are here with Paul Graham.
Hey there.
And Paul is going to enlighten us with some awesome physics knowledge. Now, we had a couple questions last week that I thought we would open up with. First one, a seemingly simple question that's not so simple.
Uh-oh.
And the question was, why do opposite charges attract each other?
Okay.
It seems like it should be an easy question to answer, but it's actually much deeper than that. And then somebody else wanted to know about Planck length. So I'm going to turn this around, give you to Paul, and let you enjoy his explanation. All right, Paul, why do opposite charges attract? Tell us.
Ah, man. I've got a serious temptation here to just say, well, they just do. You try it out, they do. That's not entirely cowardice or laziness on my part. At any moment, no matter how much humans know about the physical universe we're in, there always is a kind of a simplest, most basic layer to what we know. And at that point, we always have to say, I don't know why that's true. It seems like that's the universe we live in, but I couldn't tell you why. If I were living just after Isaac Newton, and you were to tell me, hey, when I slide this coffee cup across the table, why does it come to a stop? I would say, oh, well, I can tell you a better answer than the old Aristotelian answer. It comes to a stop because although the natural behavior of matter is to keep on moving in a straight line, in this case, there was a force pushing it the other way. And forces don't necessarily determine which way something moves. They determine which way something accelerates. And I would be all proud of myself because that would be the modern, updated, enlightened view, brushing away centuries, millennia of Aristotelian nonsense. And then the bastard asks me, okay, so why do forces cause acceleration rather than velocity? And I would have to say, I don't know. I mean, we tried it out both ways, and that's the version that works. I mean, look, I'll do some experiments. I'll show you that they do, but I can imagine a universe with completely different laws of physics. So at that moment, that was the kind of the most basic level, the most fundamental physics that we knew. So if you say, hey, why is that true? We'd have to just say, hey, that's the universe we live in. Now, as time goes on, we learn more and more fundamental physics. If you ask me today, hey, could you prove to me Newton's second law? Could you prove force equals mass times acceleration? I could say, oh yeah, sure. Let me start with general relativity, and then we'll take the limit as the curvature goes small, so we got flat space-time, and then we'll take the limit as we have very slow-moving objects. And look, the equations of general relativity simplify down and just spit out Newton's laws at that point. But then you could ask me, why is general relativity true? And I would have to say again, damn, it just is. That's the universe we live in. But general relativity right now is one of the most fundamental things we know. So we can't tell you why it's true. We can just tell you that all the evidence is that it is true. And then from there, we can, starting from that basic point, we can build up all kinds of stories about why other things are true and reason them out from general relativity. But the fact that general relativity works is just, we've done the experiments, we've looked at the universe, and as far as we can tell, it always gets things right. Now, if you had asked me 100 years or 150 years ago, why do opposite charges attract? Why do like charges repel? I would have had to give you that kind of answer. I would have said, yeah, that's just the way the rules of the universe are. We don't know why, but look, I can show you that they do.
Good question for future scope. What's the difference between general relativity and special relativity?
That is a good question.
We'll put that on hold.
We will return to that, yeah. Today, though, I actually can tell you why opposites attract, why like charges repel, because we've learned some more physics that's even more basic and fundamental than Maxwell's equations, which were the equations that kind of summed up that old classical understanding of electromagnetism in the 1860s.
So one interesting thing might be, what do we mean by charge?
Okay, so what we mean by charge
I don't know if you want to start with that. I mean, I didn't want to interrupt, but even that could be...
Yeah, when we talk about matter having charge, when we say if I rub this thing against my hair, this thing stole some negative charge from my hair, and my hair is now positively charged, and this cloth is now negatively charged. What I really mean is that it stole some electrons from my hair. The fundamental particles that make up matter are protons, neutrons, and electrons. I think we probably have the diagram up here at some point that inside each atom, you've got a central nucleus composed of a cluster of protons and neutrons. And those protons have what we call positive charge. And surrounding that, there is a cloud of electrons, and the electrons each have a little bit of negative charge. By the way, the reason why we call the protons positive and the electrons negative, totally arbitrary. It's
Benjamin
actually
Franklin
Ben
screwed
Franklin.
us.
Yes, damn you, Franklin! It wasn't his fault. They didn't know that electrons existed until 1890. Franklin did his scientific work in like 1750 something. So yeah, he had no way of knowing that when he said, hey, if I rub a piece of silk against a piece of glass, then I can see they both pick up electrical charge, and he just made up this word, electrical charge, for this weird property that they pick up. And he said, you know, I'm going to call the kind of charge that the silk picks up negative and the glass picks up positive. If he had said it the other way around, then to this day we would be saying protons are negative and electrons are positive. And that would actually be a lot easier to deal with, because since the electrons are more loosely bound, they're orbiting in this kind of loosely held cloud around the nucleus, whereas the protons and neutrons are held toward one another by one of the strongest forces that there is in nature, called the strong nuclear force, named by somebody without imagination, apparently. But what they lack in imagination, they made up for in accuracy. It is a really strong force. So there's no way in hell I can easily remove one of those protons from that nucleus. I can remove one of the electrons from that cloud. And again, you know, just as I rub my hand against my hair, I probably am stealing a small number of electrons from the cloud of electrons in various atoms in my hair and transferring them to my hand. Now, so that means my hand, having gained electrons, becomes negative. My hair, having lost electrons, becomes positive. And if that sounds backwards, damn you, Franklin. But am I allowed to insult lawyers?
Sure.
Okay.
It's my scope.
Okay. I do have a feeling that, you know, every year there is probably a small number of otherwise promising science students who just, because of all the little nitpicking things that you have to keep track of because electrons, the more easily movable charges, are negative, end up getting fed up with science in general and switching careers and becoming lawyers or marketers or something like that. Which means our entire civilization is poorer by the tune of several scientists and engineers each year converted into lawyers because Franklin made the wrong decision.
Damn you, Franklin!
Yes. Now, so this is what we mean by charge, though. If I say something has negative charge, it means literally it has an overabundance of electrons compared to protons. And it doesn't take more than a tiny overabundance. Electrical forces are strong enough that if something has 1 part in a billion more electrons than protons, that would actually be a ridiculously strong amount of negative charge to put on any reasonably sized object.
Keep it clean, Lily. Just a comment.
Oh, okay. If something has positive charge, that means it has lost some of its electrons, so it now has more protons than electrons. And again, even if it's a mismatch of 1 part in a billion, that'll be a noticeably strong positive charge. Now, it turns out that, yeah, positive and negative charges do attract each other. Positives and positives repel, negatives and negatives repel. This, by the way, is the reason why this cloud of electrons is orbiting the nucleus of the atom in the first place. They are being pulled toward that positive nucleus, so they end up orbiting around it. Now, when I say orbiting around, I'm committing all kinds of sins against quantum mechanics, because that's not a good description of exactly what they do, but they inhabit this probability cloud that's pulled in toward the nucleus by the existence of that positive charge. Now, if you were to say, why do positives and negatives attract each other? Again, for a long time, during the glory days of electromagnetism, all during Michael Faraday's lifetime, James Maxwell's lifetime, Lord Kelvin's lifetime, they would have had to just say that's just one of the rules of nature. They do attract each other, and like charges repel each other. Today, though, we can actually, in the 1930s, a guy by the name of Paul Dirac came up with a branch of physics that we call quantum field theory. And this is kind of the souped up version of quantum mechanics that you've got to use anytime you've got particles moving a decent fraction the speed of light. So when we're doing things like the accelerator experiments, the collisions in the LHC in Switzerland and all that kind of thing, definitely just the standard physics that they use for every calculation they do there would be quantum field theory, because you've got these particles moving at very nearly the speed of light, and they are individual subatomic particles. So
Here's somebody says, the reason why positive and negative charges attract is because it tends to minimize the energy of the system.
It does. But then you'd say, but now I've got an equivalent rule. Why does the energy of the system follow that particular equation? So yeah, I could write an equation for the force, and from that show you what the energy is. I could write an equation for the energy, and from that show you what the force is. But either way, you'd say, all right, why did we start with that equation? And again, at one time we would have had to just say that's one of the most fundamental rules of the universe we know about. I can't tell you why our universe follows that rule, but it does.
Well, a second comment for possible scope, entropy.
Entropy, nice one, very nice one. Yes, that will be a whole other can of worms we will open sometime. So I wouldn't even try to start talking about entropy right now, because I might not stop.
Okay, so two positive charges repel each other, two negative charges repel each other, positive and a negative charge attract. Why?
Why?
Give us some quantum field theory.
Okay, here I have got, let's say, 2 electrons. So 2 negative charges, electrons, and they are zooming along through living their lives. And if I am drawing the kind of diagram we draw in quantum field theory, time always flows upward toward the top of my diagram. So when I draw this electron moving up the board like this is actually an electron that's standing still, but hey, even if I'm standing perfectly still, I'm still moving toward the future. I can't help that. So this electron's moving just forward in time. If I wanted to draw one that was moving to the right, I might do that. Or if I wanted to draw one that was doing the slalom course, I might do that. So they're all moving forward in time, but I use that other axis to show what's going on in space, how they're moving back and forth or standing still or whatever. Now, it turns out in field theory, so when Dirac invented field theory, it turned out all kinds of things came with the rules for how to do quantum mechanics at high energies. One of the things that Dirac found was you just flat out cannot get quantum mechanics to work at these energies unless you introduce the idea of antimatter. So every particle has a antimatter mirror image type of particle. For electrons, their mirror image is positrons. For protons, it's antiprotons, and so on. Now, it also turns out that if you've got a particle that looks like it's just minding its own business, actually, it has all kinds of crazy stuff going on behind the scenes. I've heard it said to be analogous to a duck, where you watch this stately-looking duck gliding across the water, but if you watch what's going on underneath the water, it's churning its feet madly in order to keep itself moving. Well, this electron that looks like it's just kind of calmly moving forward in time, not even moving back and forth, at every moment is giving off clouds of virtual particles, they call them. Virtual particles are particles that can live only a very short time before they have to be reabsorbed because they don't have the right amount of energy to be permanent particles, or they don't have the right amount of momentum. So this could be a virtual photon here, a wiggly line. These diagrams I'm drawing, by the way, are called Feynman diagrams. Richard Feynman did not invent quantum field theory, but his way of thinking about it turned quantum field theory from something where every calculation was a painful, arduous process to something where you could turn off a bunch of calculations in an afternoon. So Feynman made quantum field theory into a usable, useful tool in physics. But yeah, these squiggly diagrams are called Feynman diagrams. Curvy line is a photon. So this photon was given off by the electron and then reabsorbed. It could also give off other things. Maybe it gives off another photon right here, and this photon maybe splits into another electron and its antimatter version. Like I said, you need antimatter to exist for this model to work at all. So this splits momentarily into an electron and a positron. Then they reannihilate back into a photon, And that photon, since it's still a virtual photon, it still has the wrong amount of energy and momentum to be a permanent part of the universe, gets reabsorbed by the electron just in the nick of time before some accountant comes along and tells it it had the wrong amount of energy. So this whole sea of frothing virtual particles surrounding every real particle is just kind of the way things work. Why is it the way things work? I don't know, actually, because while I can tell you that quantum field theory answers the question of why electrons repel each other, the question of why quantum field theory exists, why does our universe follow this set of rules and not some less crazy sounding set of rules, we don't know the answer to that. Unless you are a superstring theorist, in which case you say, of course I know the answer, it's just the low energy limit of superstring theory. But superstrings are still a work in progress. So now, why do these virtual particles come into that question of how two electrons interact with each other? Actually, here's two electrons, both going along, minding their own business, moving forward in time and not doing much else. They are each giving off this cloud of virtual electrons into the space around them, but this one can give off a virtual, or not virtual electrons, virtual photons, also virtual electrons, virtual particles in general. Feynman had a great way of putting it. He said, anything that's not forbidden is mandatory. So any intersection I could put into one of these diagrams that doesn't violate some conservation rule. On this one, if I tried to make both of these electrons, you'd say, how did it go from 0 units of charge to 2 units of charge? You just can't. Nature never does that, not even temporarily for virtual particles. So you'd say, okay, that one was forbidden. But hey, an electron and a positron coming out of a photon? Yeah, that can happen. So it will happen a certain percentage of the time. So you got this whole storm of virtual particles. One thing that could happen is this thing could give off a virtual particle, and before the universal accountant gets around to auditing the books and saying you've got the wrong amount of energy and momentum to exist, it could be absorbed by the other electron instead of the one that gave it off. This guy, meanwhile, could be giving off its own virtual particles, and again, some of them get reabsorbed by this particle, but others might again manage to cross that gap and get reabsorbed by the other one. Now, why does that matter? Well, imagine these are two skaters going along side by side on the ice, and they start throwing snowballs at each other. Well, every time I throw a snowball, I recoil. That's momentum conservation, and when Feynman said what's not forbidden is mandatory, one of the things which is not allowed, one of the things that is forbidden, is ever trying to violate momentum or energy conservation. So if I throw that snowball, I will recoil the other direction. This person over here catches the snowball, she recoils that way. So the two of us, if we're throwing snowballs at each other, could gradually start to notice that our paths are curving apart or diverging because those snowballs are pushing us apart with each throw and with each catch. One thing that's different in field theory than in real life, well, field theory is real life, but one thing that's different in field theory than in a snowball fight is you can't miss that snowball. These virtual photons have to get reabsorbed or they can't exist in the first place. So none of them ever wing over that person's head and go off into the distance. They can't. They are only temporary. They have to get reabsorbed. But this does mean that these electrons will gradually accelerate apart from each other as they exchange these photons.
So if you have a electron that emits a virtual photon and then it gets reabsorbed, it's not recoiling because of momentum conservation.
It does recoil when it emits, and the other one recoils when it reabsorbs that same amount of momentum.
But let's say we're looking at the diagram on the left with the single electron that's emitting a virtual photon.
I suppose I could kind of draw this one recoiling and then coming back to its old momentum direction, but since it's actually emitting huge numbers of virtual particles at once at all moments, kind of in every energy range, it kind of all cancels out, and it's like that duck gliding across the water. It sits here calmly at the center of this storm of virtual particles.
Got it.
Now, you may well ask, I can hear you ask, okay, this works great for why electrons repel each other. Why the hell do an electron and a proton attract each other?
Hey, Paul, why the hell do a proton and an electron attract each other?
Joe, I'm glad you asked. Insightful question. Because, I mean, it seems like if we're throwing these projectiles at one another, we gotta recoil away from each other. Now, when I was talking to you, though, in the first place about how virtual particles work, one thing I mentioned is the whole reason they are not allowed to continue existing permanently is they have the wrong amount of energy and momentum. There's a relationship. When we do more about general relativity, I might come back to the energy momentum hyperbola and show you this diagram that has this nice geometric shape that connects the energy and the momentum of every particle. A virtual particle doesn't have to follow that relationship. It can be off the hyperbola. It can have the wrong amount of energy and momentum as long as it has them only briefly. This is one way of putting the Heisenberg uncertainty principle. It says things like, oh yeah, the uncertainty in energy times the uncertainty in time can never be bigger than a constant, which is called h bar. By the uncertainty in energy, one way of thinking about that is that's how far off that energy momentum hyperbola you are. Uncertainty in time, that's how much time you're allowed to exist if you're that far off the energy momentum hyperbola. So, because these are temporary particles, this one can throw a snowball over here at her friend, and the snowball, even though it's moving this way, its momentum points the other way. That is something no real snowball would ever do. If it's moving to the right, its momentum's got to point to the right. However, a virtual particle can. It can be far enough off that energy momentum hyperbola that it actually carries the wrong momentum. So when she throws that snowball, instead of recoiling backwards, she actually recoils forwards when she releases it. Because right now you can say, I have zero momentum, and now I throw the snowball, it has momentum that way? Well, to still add up to zero, I must now have momentum this way. So if you throw one of those virtual photons with the wrong sign of momentum, you recoil toward the direction it came from. And then what happens when her friend over here catches that photon? So this skater recoiled that way. And then her friend over here, minding his own business, catches this photon. Again, the photon is moving this way, but its momentum is that way. This guy, who was just sitting here minding his own business, absorbs momentum that's now pointing that way. So he starts moving this way. By the way, because these two, the skaters, are real particles, they're not virtual particles, they got to be on the energy momentum hyperbola, that means that if he has momentum toward the electron, he will be moving toward the electron. His motion's got to be in that direction. The electron's got momentum now toward the proton. She's got to be moving toward the proton. Her motion will be that way. It's the virtual particles that can break that rule and can seem to have the wrong sign of momentum.
There's a good question I don't know if you can touch on, but somebody wanted to know, what is the mean lifetime of a virtual particle? Can we even answer that?
Depends on how far off that momentum shell it is. There's no upper bound to how long they can live, but the longer you need them to exist for,
the lower the energy.
Yeah, the closer they've got to be to having the right amount of energy and momentum for a real particle. You could think of this as possibly one reason why forces get weaker with distance is if I'm trying to exchange virtual photons with something that's far away from me, those photons have got to be really close to the right amount of momentum and energy for real particles. If I'm trying to exchange virtual photons with something that's right next to me, they can be a lot smaller.
Somebody just said a good thing. People seem to get the whole why they repel. Can you do a little recap again on why exchanging particles can actually cause them to attract?
Okay, this is something that can only work for virtual particles. And hey, by the way, for the person who asked what's the lifetime of these things, again, I can't give you an upper bound. I can't even give you a mean lifetime, which is what I know you asked for, and I feel ashamed that I can't answer that. But I can tell you, if this delta E is kind of how wrong is the energy of that particle, how far is it from that energy momentum hyperbola that it's supposed to be on, this delta T then would be the amount of time that it's allowed to exist in that state.
And you want to give people an order of magnitude for h bar?
Yes, this is one of those built-in constants of the universe. It's the one that you always get when you're doing quantum mechanics, and its value is roughly 6 times 10 to the negative 34. So it's a tiny number, and its units are joules times seconds. So again, this is saying if you've got a virtual photon which is any distance at all off of that energy hyperbola, then the amount of time it's going to last is going to be a really, really tiny amount of time. However, again, if you put it close enough to the hyperbola, you can make this number so tiny that your time doesn't have to be all that small anymore, and you can get virtual photons that last for a longer and longer time.
So you can't really answer the question because they can exist for
Yeah.
any amount of time.
Yeah, although she did say mean, so that would say, all right, well, average it out over a whole distribution of possible energies, and I have never actually thought of that. I don't know whether that's possible or not, and if it is possible, I don't know how to do it, but I'll give that some thought.
If anybody can figure it out, you can.
But
So you want to recap how exchanging?
Yeah, so here again are my two skaters.
Can you write that a little bit bigger?
Okay, two skaters, an electron, negative charge, and a proton or a positron or anything with positive charge. They start out both just moving along, minding their own business, moving toward the future, but not doing anything else. And the electron emits a virtual photon. This photon, it's moving to the right. It's moving toward the positron over here. Its momentum, though, could be in either direction. Again, this one might have momentum, which is toward the left.
And usually an object's momentum points in the same direction as its velocity.
Yes, a real-life snowball, there I go saying real life again, a non-virtual snowball, which I throw, if it's going that way, its momentum points that way. But again, the virtual particles in field theory, they can get their momentum wrong, just like they can get their energy wrong. And when I say wrong, it means it would be the wrong amount for a real particle. It's not the wrong amount for a virtual particle, obviously, because they're there and nature is perfect. But this thing, this photon, zings off away from the electron, and if its momentum is pointing in that unexpected direction, see, there's a better word than wrong, that unexpected direction to the left, then when this electron lets go of the photon, well, it now has momentum to the left. The electron has to pick up momentum to the right to balance. I mean, just like if I throw a real snowball, I give it momentum in that direction, and I pick up momentum in the other direction to balance that, and recoil. In this case, the recoil's backwards. The electron recoils in the direction that you threw the photon, instead of away from that direction.
So it'd be like you throwing a snowball in one direction and also moving in that direction.
Yes, I throw the snowball, and somehow, just sheerly through this recoil effect, instead of me recoiling backwards, I kind of follow along after the snowball. Now you could say, well, yeah, you could do that if you push against the ground, but I'm saying, no, the electron's not pushing against anything. This is purely from that internal recoil. This is what happens when momentum's pointing the unexpected direction. Now,
Somebody just said Lily, I love your comments. I just threw a tennis ball at my dog. He wasn't repelled. He came running towards me. I've disproven physics.
Number one, that is awesome. And number two, just if you wanted an actual physics answer to that, you'd say, okay, but your dog was pushing against a third object, the floor. These guys aren't doing that.
Lily 1, physics 0.
That is awesome. But then similarly, when this proton or positron or whatever I'm making this positive particle over here catches that photon, well, the photon is not carrying rightward momentum, it's carrying leftward momentum. So even though it came in from the left, this guy recoils toward the left. Now I'm making the recoil look much bigger than it is for a single virtual particle, but again, if I've now got a whole storm of virtual particles going back and forth, what I would do is I would set up the Feynman diagrams. I would use Feynman's tricks that he developed in the 1940s for showing how do you turn these Feynman diagrams into a calculation that you can do. And at this point, I've got to say trust me on this part. When you run the calculations, you do find that, for two particles of like charge, the dominant effect is from virtual photons which have their momentum pointing in the expected direction. For two particles with unlike charge, the dominant effect is from virtual photons that have their momentum pointing in the unexpected direction. and the charges recoil toward one another instead of away from one another. But it's not a single virtual photon that does this, and the paths don't suddenly bend like that. You'd find the paths gradually curving as this entire storm of zillions and zillions of virtual photons go back and forth.
Wow.
That is, now, you could still say, in the end, I just answered because nature works that way. Because I can't tell you why quantum field theory is a thing. Why does our universe follow this set of rules and not some other set? Come back in 50 years and we'll be able to tell you. But what we'll say is, oh yeah, well we've learned this new thing that we didn't know about back then, and now we've got this even more fundamental layer of knowledge, and we can use that to show you why quantum field theory works. But chances are you'll then be able to ask me, why does that new fundamental layer of knowledge work? I'll say, I don't know. That's just the kind of universe we live in. At any given moment in history, you could kind of say whatever is the simplest and most fundamental and deepest thing that physics knows about, there's no way to answer why that's true. It's just kind of, man, that's the best model we've got of how the universe works. If we ever get a better model, we'll tell you why this one works, but then we won't be able to tell you why that better one works. It just does. It's the universe.
So it doesn't look like we're going to have time to talk about Planck length.
Ah.
Can you give a 5-minute explanation of the difference between special and general relativity?
Yes.
Can you 5 minutes?
5 minutes.
I got to go in 5.
Okay.
All right.
Special relativity is, first off, special relativity is the more limited kind of relativity. When mathematicians say they're dealing with a special case of something, they mean, hey, this only works sometimes. If they say they're dealing with a general case, they mean it works under a much broader set of circumstances. So general relativity is every time you've seen any model of space-time being curved, if you look at a animation online of the geometry in a black hole and it looks like space-time is curving into this funnel shape, that is always general relativity. Because special relativity, the special relativity was an upgrade from Newtonian mechanics. It turns out Newton's laws don't work if you've got a particle going any decent fraction the speed of light. They just flat out give you the wrong answer. In fact, you could say they always give you the wrong answer, even for a slow particle, but for this particle, they give me the wrong answer out of the 16th decimal place. If I threw this thing at half the speed of light, they would give me the wrong answer, period, even at the first decimal place. If I threw it at 0.9999 times the speed of light, Newton's laws would not even be in the ballpark of telling me how this thing would behave. So special relativity is the model that you need to use when your particle has enough energy that it's moving a decent fraction the speed of light. However, it does not say anything about space-time being curved. It does describe this four-dimensional space-time that things move around in, but the space-time is a flat space-time. General relativity, which was Einstein's next big project and took him another 10 years after special relativity, this was his idea on a better way to model gravity. And what he eventually, the conclusion he came to, was that gravity is not really a force at all, not like these. In fact, we have never had any luck with building models where things exchange virtual gravitons, and that's how gravity works. Gravity doesn't seem to be the same kind of force as electromagnetism or the strong force. Gravity is the side effect of the fact that space-time is curved. Now, why is space-time curved? Well, if you mean why in the teleological sense, I could say, I don't know, it just is. That's as fundamental as we've gotten. But if you mean like why, like how does it happen? Anytime you've got energy or momentum in some location, it pulls the space-time around it into a curved configuration. Those animations you've seen of the funnel of a black hole, that concentrated mass energy at the center of the black hole is what is pulling the surrounding space-time into that funnel. That whole picture is general relativity. Special relativity says nothing specific about gravity, says nothing about the possibility for space-time to be curved. In GR, if you want to do a gravity problem, you say, first let me figure out what energy and momentum are present, and let me work out the equations for what will be the shape of the local space-time. Now that I know the shape of this curved space-time fabric, now if I send another particle through there, but it's doing its best to move in a straight line, but it's moving through this curved space-time, there's something called the geodesic equation that you can then use, which says, well, now that I know how the space-time is shaped at each point in this location, I can figure out how the trajectory of that particle worms its way along, doing its best to move in a straight line, but it can't. There is no straight line because it's in curved space. By the way, when I throw this, and you'd say, no, you fool, it didn't even try to move in a straight line. It moved in a parabola. Well, you would say, given that the Earth is pulling the space around it into this curved configuration, that parabola was actually the straightest line possible that connected the moment in both space and time where I released the pen to the point in both space and time where the pen landed. And if I had tried to go a straight line through space, it turns out once you include that fourth dimension and you look at the overall curvature of the manifold, that would have actually been an even more strongly curved line through the full space-time.
All right.
And I think we're out of time.
I think we did it. Paul, enlightening as always, thank you so much. Let me just turn this around. All right. I hope you enjoyed today's awesome episode, episode 7 of Ask a Physicist Anything. I love listening to Paul and his explanations. We do this every Wednesday, 3 o'clock Pacific Standard Time. My name is Joe, and what's today? Wednesday, Thursday, Friday, Saturday. Awesome. Cheers, fellas. Thank you both. You are so welcome. Thursday, Friday, Saturday, I'm doing some personal development success tips from Success Magazine, so check it out. Thank you so much for joining, and hopefully we'll see you next week, if not sooner. Lily, thank you. You are a regular. Love your comments. Take care and have a wonderful Wednesday.